Hi everyone. In this video, we're going to be sketching the graphs of rational functions. But before we sketch the graph, we need to find the characteristics of the graph. So let's review. Step one, you want to factor the numerator and the denominator if you can. Sometimes they're not factorable, or sometimes they're already factored. And then once you have your factors, remember that the domain is always x cannot equal the zeros of the denominator. These are the values where the function is undefined because we cannot divide by 0. So these are also the values where the graph has either a hole or a vertical asymptote. Okay, so where does the hole occur? The hole occurs at the zeros of the numerator and denominator. So if a number is a 0 of both the numerator and denominator, then that is the location or the x-coordinate of the hole. Recall, to find the y-coordinate of the hole, you would just plug into the simplified form of the rational function. Okay, now, the vertical asymptote occurs at the zeros of the denominator only, okay, meaning it's only a 0 of the denominator, not both the numerator and denominator. All right, and then the x-intercept occurs at the zeros of the numerator only. Okay, now for the last two, the horizontal asymptote and the y-intercept, you actually want to look at the non-factored form of the polynomials. And to determine the horizontal asymptote, this is where you compare the degrees. Okay, there are two things that could happen for the graph to have a horizontal asymptote. Either the degrees are the same, or the degree of the denominator is bigger. When the degrees are the same, that is when you divide the leading coefficients. When the degree of the denominator is bigger, then the HA is y equals 0. Okay, and then for the y-intercept, this is where you divide the constant terms. Okay, let's look at some examples. Okay, so here we are given x squared minus x minus 6 over x squared minus 9. So again, we're going to start by factoring the numerator. Okay, this is going to factor into x minus 3 times x plus 2. And then the denominator will factor into x minus 3 times x plus 3 using difference of squares. Okay, so remember, domain, we'll start there. X cannot equal the zeros of the denominator. The zeros of the denominator are positive and negative 3. Okay, the next thing I would look for is, do we have any zeros of both the numerator and the denominator? Well, notice the x minus 3 over x minus 3. That means the x coordinate of the whole is positive 3. The y coordinate of the whole, to find the y coordinate of the whole, we're going to plug 3 into the simplified form of the rational function, which is x plus 2 over x plus 3. So we plug in 3, we're going to get 5 over 6. Okay, now see how the x plus 3 is still left in the denominator? That means the VA is at x equals negative 3. And the x plus 2 that's in the numerator, that's your x-intercept. So the x-intercept is negative 2, 0. Okay, now we're going to go back to non-factored form. So for your horizontal asymptote, compare the degrees. They are the same. So you divide the leading coefficients. 1 divided by 1 equals 1. And then for your y-intercept, you divide the constant terms. Negative 6 over negative 9 simplifies to 2/3. So 0 2/3 is your y-intercept. Okay, now let's see if we can put this into a sketch. All right, so I like to start with the asymptotes. So we have a vertical asymptote at negative 3. We have a horizontal asymptote at 1. And then our x-intercept is negative 2, 0. And our y-intercept is 0 2/3. So I don't know, about right there. And then our hole is at 3, 5, 6, getting closer to 1. So I'm going to squeeze that hole in there. Make sure you put an open circle for your hole. And then don't forget what your parent function looks like, okay? A lot of these graphs look pretty close to 1 over x. So just recall that the parent function looks like this. So this graph is actually pretty close to the parent function. The graph is going to go through the intercepts and approach the asymptotes. And you just want to jump over the hole. So we know that part of the graph looks like that. Now there's another part of the graph to the left of the vertical asymptote. And again, just kind of knowing what our parent function looks like, I can pretty much tell that it's going to look like this. The other option would be that it did this, but we don't have another x-intercept, so the graph can't cross the x-axis, again, if I don't have an x-intercept there. So I pretty much know that that part of the graph would have to be above the horizontal asymptote. Yeah, so this is what the graph would look like. Okay, let's look at another example. Okay, let's start by factoring. So the numerator is going to factor into x plus 4 times 2x minus 1 over x plus 2 times x minus 1. Okay, let's run through our characteristics. So the domain is x cannot equal negative 2 or 1. Okay, and again, the next thing I would look at is, do we have any factors the same in the numerator and the denominator? We do not, so that tells you there is no hole, which means there's actually 2 vertical asymptotes. Okay, there are 2 x-intercepts which come from zeros of the numerator. So negative 4 is 0 and 1/2 0. Okay, and then for your horizontal asymptotes, compare the degrees. They are the same. So you divide your leading coefficients. 2 divided by 1 equals 2. And then for your y-intercept, divide the constant terms. So 0, 2 is our y-intercept. All right, let's try to sketch the graph. So this one has two vertical asymptotes, one at -2 and one at 1. And then our HA is y equals 2. And then our x-intercepts are -4, 0, and 1/2, 0. And our y-intercept is 0, 2. Now, you might be thinking, wait a minute, I thought a graph couldn't cross a horizontal asymptote. Well, it actually can. So typically a graph will not cross or touch a vertical asymptote because those are the x values where the function is undefined. But since a horizontal asymptote really describes end behavior, and we know the graph is going to approach the horizontal asymptote on the left end and the right end, sometimes in between those two vertical asymptotes, the graph can actually cross or maybe even touch a horizontal asymptote. Okay, guys. Now, this one is a little bit more complicated because of the two vertical asymptotes. That means there's actually going to be 3 parts to the graph. One thing that can be helpful is the 2 outer regions. That's where the graph looks pretty similar to the parent function. So I can kind of tell based on the x-intercept -4, 0, that this part of the graph is going to look like this, because I know the graph is going to go through that point. Well, and we know it's going to cross through that point and then approach the asymptotes. And then to the right of that second VA, I can kind of tell the graph is going to look like this because there's no x-intercept in that region. So the graph would have to be above the horizontal asymptote, because if the graph is below the horizontal asymptote, it's going to cross the x-axis. Okay, now what's happening in between the 2 vertical asymptotes? Here's where I might plot an additional point just to see that shape a little bit better. So why don't we plug in -1 for x and just find what that y coordinate is. Now, when you plug in for x, you can plug it into non-factored form or factored form. I'm going to plug it into factored form. So we'd have -1 plus 4 times, well, 2 times -1 is -2 minus 1 over -1 plus 2 times -1 minus 1. Okay, that'll simplify to 3 times -3 over 1 times -2. And then that'll simplify to -9 over -2, which will equal +9 over 2, which as a mixed number is 4 and 1/2. So if I plot that point, -1, 4 1/2, it's like right here. And so now you can kind of see that shape taking place. The graph is going to go through those 3 points, but it's also going to approach the asymptotes. Okay, one more example. All right, so again, let's start by factoring. So the numerator is going to factor into actually x minus 1 squared, or x minus 1 times x minus 1. And then for the denominator, we can just factor out the x squared. Okay, so our domain is x cannot equal 0 or 3. And we don't have any factors the same in the numerator and the denominator, so there's no whole, which means there's 2 VAs, again, at 0 and 3. Your x-intercept, which comes from the zeros of the numerator, is going to be 1, 0. But see how it's x minus 1 squared? The multiplicity of the 0 also works with the graphs of the rational functions. So like we said with polynomials, like the 0 is 1 with a multiplicity of 2, which tells us the graph only touches the x-axis at that point. Okay, in And then the horizontal asymptote, compare your degrees. Degree of the denominator is bigger, so it's y equals 0. And then for your y-intercept, you're going to divide the constant terms, but the constant of the denominator is 0, and 1 divided by 0 is undefined. So that tells us there's no y-intercept. All right, so let's try to sketch this thing out. We're going to put in our V8s and our HA. And then we're going to plot our points. So we have 1, 0 as an x-intercept. Now we know the graph only touches at that point. So the graph could come up, touch, and go back down, or it could come down and go touch and go back up. So I feel like we probably need to plot an additional point there in between the VAs just to tell. So I would probably plug in 2 for x and then find y. And if we do that, we're going to get 1, because 2 minus 1 is 1, 1 squared is 1, over 4, 2 squared is 4, times negative 1, which equals negative 1/4. So 2 negative 1/4 is kind of, about right here. So I can kind of tell the graph is actually going to do this. And then remember, in the outer regions, it's going to look more like the parent function, but because we don't have a lot to go by, I would probably plug in some additional points. So like, let's say we plugged in negative 1 this time, we would get negative 2 squared, which is 4, over, well, negative 1 squared is 1 times negative 1 minus 3, which is negative 4. That'll simplify to negative 1. So negative 1, that point is right here. So that tells me the graph looks this. And then I might even plug in positive 4, which is to the right of the second VA. So if we do that, we'll get 4 minus 1, which is 3. 3 squared is 9. Okay, 4 squared is 16, but then times 4 minus 3, which is 1. So we get 9 over 16, which is pretty close to a half, but it is a positive y value, so that tells me the graph is going to look like this. So we did have to plot, some additional points on this graph, but, we were able to get a pretty good sketch of it without plotting a whole bunch of points. So, all right, you guys, we will definitely practice this in class. As always, thank you for watching.